100, and today I'm going to go over the Stokes-Einstein relationship in a step-by-step derivation. So, just a conceptual overview, I just want you to imagine you swimming through a pool. That resistance you feel while you're swimming is a drag force, and drag force is experienced by having a viscous liquid. The more viscous, the more resistance you'll feel. And the viscosity is actually more important than how fast the object is actually moving. And the spherical coordinates on there are kind of like latitude and longitude on the globe. It's pretty similar to that. And string functions is a spherical coordinate, and it basically helps you understand how the water is actually moving on the ball itself. So the way it's derived, we use nabla P is equal to mu nabla squared V, where P is pressure, mu is the dynamic viscosity, and V is the velocity field. We use a couple of assumptions, such as that time is independent and gravity is also neglected, and there's also symmetry. And by deriving this, we use psi, and we express this as velocity and pressure fields. And then we simplify that equation using boundary conditions such as velocity equals v at infinity and 0 at the sphere's surface. And then we determine that by using psi that satisfies these conditions. And then we end up with the equation F is equal to 6 pi mu A and V, and that's known as a Stokes law. So now to conceptualize the Einstein, he used something called the random walk. He thought about how particles move in a fluid as if they're taking random steps in different directions. This is called random walk. We use something called mean squared displacement to measure how far these particles move on average. It helps to understand diffusion, like how a drop of food coloring spreads in water. So Einstein's big idea was to link this random movement to how quickly and widely particles spread out in a fluid. So when you see something like sugar dissolving in tea, it's all about how these tiny particles are spreading out randomly, and this concept helps us to get why and how diffusivity happens. So moving on how to he mathematically described diffusion. The formula he used was delta x squared, which is equal to 2n dt, where the delta x is, this is the mean square displacement, d is the diffusion coefficient, and n is the number of dimensions, and t the time. So basically, what Einstein did with this formula is he connected tiny random steps of particles with how they spread out over time. This formula helps us understand the bigger picture of diffusion, like how a small moves through a room. It's all about linking these small random movements to overall process of spreading out. So lastly, we're combining Stokes and Einstein. So let's combine these two equations. We got the drag forces from the Stokes and showing us how fluid slows down a particle, and Einstein's diffusion theory explaining how particles spread out in a field. The Stokes-Einstein relation links these two by a neat formula called D is equal to kBt over 6 pi mu and A. Here D is the diffusion coefficient, Kb is the Boltzmann constant related to temperature, T is the temperature, mu is the fluid's viscosity, and A is the particle size, and this formula tells us how fast particles spread out in a fluid. And based on temperature, fluid thickness, and particle size, and this is how combining a different scientific ideas gives us a better understanding of natural phenomena like how medicine disperses in the body or how pollutants spread in the air. Thank you very much.